Equations, Level 1. An equation is formed by placing an equal sign between two numerical or variable expressions. Each equation contains two sides, the left-hand side and the right-hand side. In algebra, equations are a type of mathematical sentence that can either be open or closed. Examples of closed sentences are the following numerical expressions. A closed sentence is always true or always false. In the first equation, the sentence is always true. 3 plus 5 is equal to 8 is always true. In the second equation, the sentence is always false. 4 plus 4 is equal to 10 is a false statement. Equations containing variables are called open sentences because of the fact that they can either be true or false depending on the value of the variable. Examples of open sentences are the following variable expressions. The equation 5x plus 1 equals 11 and the equation y plus 5 equals 5 plus y. At times, the values that a variable can attain can be restricted to one or more numbers. The set of numbers that a variable may represent is called the domain. As a consequence, a variable in an equation can be replaced by any of the numbers in its domain. Remember, the resulting equation may be either true or false. In algebra, the way we denote a set of numbers is by enclosing them using braces. For example, a short way to write the set whose members are 1, 2, and 3 is as follows. Moreover, this set also corresponds to the domain of a specific variable. In this example, the domain consists of the numbers 1, 2, and 3. Okay, say we have the following equation. 6x minus 1 equals 17. And we are asked to solve this equation over the domain 2, 3, 4, and 5. In other words, the variable x is a set whose members are 2, 3, 4, and 5. The way we mathematically represent the domain is as follows. This expression is read as x belongs to the set whose members are 2, 3, 4, and 5. It can also be read as x is an element of 2, 3, 4, and 5. The purpose of this problem is to find the solution set of the equation over a given domain. Any value of a variable that turns an open sentence, in this case the equation, into a true statement is a solution or root of the equation. In other words, it is said to satisfy the equation. So the main goal of this problem is to find the values of x from the given domain that yields a true statement. The easiest way to solve this problem is by creating a table as follows. The first column will contain all the elements of the given domain. In this case, 2, 3, 4, and 5. The second column is where we will substitute the given elements into the equation and evaluate them at the given number. The third column will contain the simplified equation. In the last column, we'll keep track if the resulting substitution yielded a true or false statement. Okay, so let's systematically go through each element to find the solution set. The first element in the domain is the number 2. So we substitute that into the equation and evaluate it at that given number. This results in the statement 11 is equal to 17, which is false. Let's evaluate the second element in the domain. In this case, it's 3. And substituting it yields the statement 17 is equal to 17, which is true. The third element is 4. So substituting it into the equation yields the statement 23 is equal to 17, which is false. Now the final element of the domain is 5. Substituting it into the equation yields the statement 29 is equal to 17, which is false. Alright, our job is to find all solutions of the equation from the elements of the given domain. Looking at the final column, we see that the only element that yielded a true statement was the number 3. Therefore, the solution set is the number 3. The way you mathematically represent the answer is as follows. We use 3 dots arranged in the form of a triangle. This symbol is read therefore. And the solution or roots of the equation is enclosed in braces, like this. We conclude that the solution set is equal to 3. Be aware that some equations may have more than one solution, and some equations may have no solutions at all. An example of an equation that has more than one solution is the sentence x plus 2 is equal to 2 plus x. This equation is true no matter what number is substituted for x. In the end, the solution set to an equation depends on the elements of the domain that are given. Alright, in our next video we will go over more examples in finding the solution sets of equations over a given domain. Equations, Level 2. Alright, let's work on the following examples. Solve the equation x plus 5 is equal to 11 if x is an element of 0, 2, 4, and 6. Like in the previous video, let's set up a table as follows. The first column will contain the elements of the domain, in this case 0, 2, 4, and 6. The second column is where we substitute the variable of the equation with its respective element. The third column will contain the simplified equation after substituting the elements into the equation. And lastly, the final column will keep track if the statement obtained is either true or false. So substituting the first element of the domain into the equation and simplifying yields the statement 5 is equal to 11, which is absolutely false. Next, we substitute the second element of the domain, in this case 2, into the equation, which simplifies to the statement 7 is equal to 11, which is false. Moving along, we substitute the third element of the domain, the number 4, into the equation, and simplifying the expression yields the statement 9 is equal to 11, which is also false. Lastly, we substitute the final expression of the domain, in this case the number 6, into the equation, and then we simplify the expression, which reduces to the statement 11 is equal to 11, which is a true statement. Looking at the results, we see that only one element in the domain yielded a true statement. Therefore, the solution set is 6. Alright, let's try the next example. Solve the equation x times the quantity 3 minus x is equal to 0 if x is an element of 0, 1, 2, and 3. Alright, just like the previous problem, let's set up a table and start systematically substituting the elements of the domain into the equation. The first element is 0, so we substitute that into the equation, which yields the statement 0 is equal to 0, which is a true statement. The second element of the domain is 1, so substituting that into the equation yields the statement 2 is equal to 0, which is false. The third element is 2, so substituting that into the equation yields the statement 2 is equal to 0, which is also false. Lastly, the element 3 is substituted into the equation, which yields the statement 0 is equal to 0, which is true. Looking at the results, we see that two elements of the domain yielded a true statement. Therefore, the solution set is 0 and 3. Notice that in this example, the equation had more than one solution or root that satisfied the equation. In other words, the element led to a true statement. Alright, let's try the next example. Solve the equation z plus 5 is equal to z plus 5 if z is an element of 0, 1, and 2. Once again, we set up a table as follows, and systematically go through each element of the domain. So substituting the first element, we have the statement 5 is equal to 5, which is a true statement. The second element is the number 1, and substituting that into the equation yields the statement 6 is equal to 6, which is also a true statement. Lastly, the third element of the domain is the number 2. Substituting it into the equation yields the statement 7 is equal to 7, which is also a true statement. Notice that every single element in the domain yielded a true statement. Therefore, the solution set is 0, 1, and 2. Let's try the next example. Solve the equation 2x equals x plus 7 if x is an element of 0 and 1. Notice that we only have two elements in the domain. Like always, let's create a table and substitute each element of the domain into the equation. Substituting the first element into the equation and simplifying, we have the statement 0 is equal to 7, which is false. The last element in the domain is 1, and after substituting it into the equation, we have the statement 2 is equal to 8, which is also false. Looking at the results, we see that there isn't a single element in a domain that yielded a true statement. This means that the equation has no solution over the given domain. In this example, there wasn't an element in the given domain that yielded a true statement, meaning there wasn't a solution or root that satisfied the equation. Recall that the solution set is dependent on the domain given. For example, if we work with the same equation, but with a completely different domain, say the domain that contains the elements 6 and 7, we would obtain a completely different answer. So let's try it out. Substituting the first element into the equation yields the statement 12 is equal to 13, which is a false statement. The last element yields the statement 14 is equal to 14, which is a true statement. Looking at the results, we see that only one element yielded a true statement. Therefore, the solution set is equal to 7. Notice that the solution to the equation is dependent on the domain for which we are solving the equation. This is an important concept that many students from higher level mathematics, such as calculus and differential equations, tend to forget. Alright, In our next video, we will learn how to translate written words into numerical and variable expressions.